Faraday's laws of electromagnetic induction describe the relationship between electricity and magnetism, specifically how a changing magnetic field can induce an electromotive force or EMF in a conductor. So let's explore both laws in detail with an example. Faraday's first law. A change in magnetic field within a closed loop induces an electromotive force, or EMF, in the wire. This law states that if the magnetic flux through a closed loop changes over time, an EMF is induced in the loop. The greater the change in flux, the greater the induced EMF. Faraday's second law. The induced EMF is directly proportional to the rate of change of magnetic flux through the loop. Alright, so let's dive into the mathematical expression of Faraday's second law. The electromotive force, or EMF, can be represented as EMF equals negative d phi sub b over dt. Here, phi sub b is the magnetic flux. Magnetic flux is determined by the magnetic field strength, the area of the loop, and the angle between the field lines and the normal to the surface. Now let's consider an example. Moving a magnet through a coil. Imagine a simple experiment where a coil of wire is connected to a voltmeter. When a bar magnet is moved toward and away from the coil, we can observe some interesting effects. First, let's talk about the initial position. When the magnet is stationary relative to the coil, there is no change in magnetic flux through the coil, and thus no EMF is induced. In this case, the voltmeter reads 0. Moving the magnet towards the coil. As the north pole of the magnet approaches the coil, the magnetic field strength inside the coil increases, leading to a change in magnetic flux. According to Faraday's first law, an EMF is induced in the coil. The direction of the induced current will be such that it opposes the change in flux, which is Lenz's law. In this case, the induced current flows in a direction that creates a magnetic field opposing the approach of the magnet. Maximal induction. When the magnet is closest to the coil, the rate of change of flux is at its maximum, resulting in the highest induced EMF. When the magnet is pulled away from the coil, the magnetic flux decreases. The induced EMF will again be present but will have the opposite direction to that when the magnet was approaching. The voltmeter will show a negative reading, indicating that the induced current flows in the opposite direction. Conclusion. Faraday's laws illustrate the fundamental principle behind many electrical devices, such as electric generators and transformers. This phenomenon of inducing EMF through changing magnetic fields is crucial for converting mechanical energy into electrical energy and is foundational in electrical engineering and physics.